Welcome to my kitchen. So here I have 2 cups. Each of these cups has a straw glued to the bottom of it and a hole drilled in the bottom of each cup. So water, if I fill up the cup with water, water can drain out through the hole and through the straw and out the bottom of the straw. One of the cups has a very long straw attached to it, and the other one has a very short straw. So what we're going to do, we're going to set up a race. Who likes live demos? Who likes a race? The suspense will be intense. So what we're going to do, we're going to fill up each cup. I'm going to let them go at the same time, and when we do so, you should pause and ponder and think, which cup is going to drain first? The one with the long straw or the one with the short straw? And of course, you should be thinking all the while about steady-state conservation of energy. All right, so the race is set up. Start your engines. Ready, set, go! And we have a victor. So, who won? Actually, the long straw won. Is that what you predicted? Well, maybe not. So, think about what your prediction was. Think about all of the terms in steady-state conservation of energy, and perhaps we can do some fluid mechanics. Let's go. So let's solve the mystery of the bottle draining. Or I guess in our case it was cups. In a previous version I had bottles. So let's solve the mystery of the bottle draining. To try to predict why the bottle or cup or whatever with the longer straw actually drained faster than the one with the shorter straw. So let's sort of sketch out what our system looks like, and then we'll proceed. And spoiler alert, this is going to be essentially an example problem where we can use conservation of energy to help predict flow velocities and things like that. So we have this cup or this bottle draining through a straw that's inserted through the bottom. So let's say we have a bottle or a cup or something like that, and then we have a straw that sticks out of the bottom. Let's say we actually know let's say we know a lot of the parameters of the system. So for example, let's say we know the diameter of the bottle. Let's say we know the diameter of the straw. These are all things that I could take out a pair of calipers and I could measure. Let's say I know the fluid depth in the cup. I'll call it little h. And let's say I also know the length of the straw, L. I know that G is pointing downwards. And I know that this whole cup straw situation is filled with water, and I know that's its density, and I also know its viscosity. So let's say these are all parameters that I know about the system that I could measure with a pair of calipers, or I could look up the properties. So these are essentially all knowns about the system. What we want to know is we want to use these parameters, all of these sort of known parameters of the system, to essentially predict what is the outlet velocity of this thing. And perhaps if we look at how the outlet velocity might be different for different straw lengths, then that might inform why the short straw draining situation took more time than the long straw situation, and in a way that was perhaps violated some of your intuitions. So if we wanted to put some actual numbers to these, again, I don't think these are the exact numbers that existed in my cup straw situation, but they are numbers that existed in a earlier version of this demo that I did where I had a bottle, but whatever. We can basically put our knowns here. Let's say the bottle is a 7 centimeter diameter bottle. Let's say the straw is a 6 millimeter diameter straw. We know G is 9.81 meters per second squared. You can look up the density of water, and it's about 1,000 kilograms per cubic meter. And you can look up what the viscosity of water is, and that's 10 to the minus 3 Pascal seconds, or kilograms per meter second, if you want to use that. We're going to look at two different versions of L. So we're going to look at one version of L where the straw is 14 centimeters long, or another version of it where it's just 1 centimeter long. And let's also look at three different values for H. And H towards the beginning of the situation, towards the beginning of the bottle draining situation, where it was basically full, and it was, let's say, about 22 centimeters. 22 centimeters deep, sort of a midway full situation where it's about 10 centimeters deep, and then a nearly empty case where we have, let's say, just 4.5 centimeters 4.5 centimeters left. We're almost empty. So we're going to look at these three situations here, and for sort of each of these three, full, mid, or empty, for each of these straw lengths, we're just going to sort of look at what the outlet velocity would be in all 6 of those combinations, and that might inform, that might inform us about why the short straw one drained faster than the long one. So what might be an appropriate problem-solving strategy? Well, I already kind of hinted at the beginning that we're going to use conservation of energy, but in this situation, if we have flow through tubes, and that flow could be potentially, have viscous losses, be turbulent even maybe, we might consider, hey, we might be worried about viscous losses in this tube. We're also considering essentially an exchange of gravitational potential energy when it's up here in the bottle or in the cup, down to kinetic energy at the outlet, as well as viscous losses as it goes through the tube. So, if we think, if I'm some little particle of water, I'm up here, I have a lot of potential energy, I'm flowing through the straw, dissipating some energy in the process, and then leaving with some kinetic energy. We're exchanging potential energies, viscous losses, and kinetic energies throughout this whole process. So if we're thinking about those sort of things, this informs us. Let's try to use conservation of energy to solve this problem, and we can't use straight up Bernoulli because we anticipate appreciable viscous losses in the straw. So what does that mean? We're going to use engineering. We're going to use engineering Bernoulli, and if we think about using engineering Bernoulli, we might have a set of assumptions that we need to keep track of. So what assumptions do we invoke in Bernoulli? Well, I guess it goes without saying that we assume that the water is incompressible and that density is a constant. If we're just sort of considering, we're considering water here, and we're talking about sort of some single viscosity, we're assuming that it's a Newtonian fluid. If we're going to use the engineering Bernoulli equation, so strictly speaking, this flow is unsteady, right? If I took a snapshot at the beginning and then came back a little while later and took a snapshot, the outlet velocities are different, the heights are all different. But it turns out that, compared to the time scale of a fluid particle zipping through the straw, like over that very short time scale, the flow is steady enough to to use this conservation of energy equation. And again, we can clarify later, under what circumstances it would be appropriate to make this. But that's a little beyond the scope of what I want to get into now. So we'll just say steady enough. Steady enough to use this this engineering Bernoulli equation. So there we have it. So we'll add a couple assumptions to this list of assumptions as we go on, but for now we have enough to start with engineering Bernoulli. So let's put engineering Bernoulli down on the page, and then let's see, perhaps we might want to make some additional assumptions or simplifications to it to make some progress. So let's work it out. So engineering Bernoulli, we have this W dot S, which is the shaft work, divided by little w, which is the mass flow rate, plus this E hat sub V, which is the viscous loss per unit mass term. Again, my previous lecture has, I go into detail on all of these terms, and that's equal to 1/2 this bracket V in cubed over bracket V in minus bracket V out cubed over bracket V out, where these brackets signify averages over the cross sections of the inlet and outlet. We also have, and this is essentially our kinetic energy per unit mass term. We also have the potential energy per unit mass term, which is G times H in minus H out, where these H's aren't exactly this H here, but we'll need to sort of define them in just a minute. And then we have plus 1 over rho P in minus P out, where these P's are pressures, and this 1 over rho is 1 over the mass density. So here we have our engineering Bernoulli equation. We have some terms that we might be able to make some progress with canceling out. So let's see if we can proceed with doing that. All right, one of the first terms that we might be able to square away or get rid of is this term right here. If you recall, this was the shaft work term. So if we assume that, if we look at the system, we don't have any pumps. It's not like I stuck a little secret pump in the long straw one, right? There wasn't a secret pump in there. Really, I swear, there wasn't a secret pump in there that was pumping that fluid faster. So we don't have any pumps or turbines. So we can get rid of this term. Another term that we can actually get rid of is this term right here. And if we think about it, the pressure at the inlet is essentially what's, I guess we need to define an inlet and an outlet. Oh my goodness, shame on me, I put this without defining an in and an outlet. So, and I didn't even define my control volume. Oh my goodness, what a disaster. Anyway, let's define our control volume. So, I'm going to call this surface right here my inlet, and it's going to be just below the water level, right? So there's some water level here, and I'm going to put my inlet sort of just below that water level. But I'm going to put it stationary. I'm going to have it stationary, but just below the water level. And here, as my outlet is going to be coincident with the part of the straw where it's going out. And the rest of my surface I'm going to make coincident with the walls of the straw or of the bottle. So that's my control volume right here that I've outlined in purple. Inlet, outlet, and everything else is the walls. So here I am. If I think about what simplifications can we make to this term, pause and ponder. Why are we able to cross off? Why are we able to cross off this term here? So perhaps you've paused and pondered. It turns out that, if I think about what's going on here, this top part of the surface is basically exposed to atmosphere up here, and after the water leaves the outlet, right as the water leaves the outlet, that water is also exposed to atmosphere, sort of on both sides, right? So if we have jets that are kind of exposed to atmosphere all around, we have pressure, we have atmospheric pressure up here, atmospheric pressure down here. The pressure at the inlet and outlet are actually the same, so they cancel each other out in this term. And it doesn't really matter if we're working in gauge or absolute pressures, whatever it is, those pressures are the same and they cancel out. All right, so here we are, making progress, canceling out terms and all that stuff. So I guess we should add atmospheric pressure at inlet and outlet to our assumptions, and no pumps or turbines also to our list of assumptions that we're going in. Now, in general, we know that flow through pipes, there's actually no flow right at the wall of the pipe, but then there's some sort of velocity profile, strictly speaking, a non-uniform velocity profile within the pipes. But in order to really make any appreciable progress in this problem, I think we need to assume uniform velocities at the outlet as well as the inlet. So let's add uniform So let's add the assumptions of uniform velocities at our inlet and at our outlet. Of course, they're not necessarily going to be the same as each other, but they will be. But across either the inlet or the outlet, we'll have those velocities present. So if we make this uniform velocity assumption, that's basically saying that this average of v cubed divided by the average of v essentially simplifies just to v squared. And that means, instead of dealing with some non-uniform velocity profile, we can kind of characterize it with a single velocity at the inlet and a single velocity at the outlet. All right. So there you have it. So that's going to help us make some progress here. So let's keep what we have kept, and square some more stuff away. So we have our viscous loss term, and that's basically equal to 1/2 v in squared minus v out squared. And of course, the v out is basically what we were looking for right here. I guess. But now we can make a little bit of progress with our potential energy. If I think about it, let's basically just define, when defining potential energy, if you think back to your mechanics problems, you're free to define your z equals 0 anywhere you want, so long as you use that same z equals 0 everywhere. So here, let's put z equals 0 right at the outlet here. So if that's the case, then h out is basically going to be 0, and h in is L plus blue h, right? So in that case, my inlet height is basically up here. My outlet is at z equals 0. So h in minus h out is basically going to be L plus blue h. And g is, of course, also a known constant. So what does that mean? It's basically g times h plus L right here. And of course, this last term is 0. So what does this mean? I've made a lot of progress. I haven't totally squared in what this inlet velocity is yet, and nor have I squared away what these viscous losses are. But compared to what my original conservation of energy equation was, man, we've done pretty well for ourselves. So now let's work on these last two sort of as of yet unknown or still to be determined terms in our conservation of energy equation. So if I think about the velocity at the inlet, that surface was moving. It was moving pretty slowly, granted, but it was moving nonetheless. But the precise speed with which this surface was moving is related to the velocity of the fluid at the outlet. Again, the faster the fluid is moving at the outlet, the faster the fluid is going to be moving at the inlet. They're not necessarily the same as each other, but they're related, right? So there's some as of yet unknown velocity at the inlet that I guess we got to treat as an unknown, right? We still haven't yet dealt with it. So in this case, the velocity at the inlet and the velocity at the outlet, we can relate to one another with conservation of mass, right? And I could go through the whole details of defining the control volume and doing v dot ends and all of that stuff, but I'm just gonna, in the interest of time, cut to the chase here. And if we applied conservation of mass, if you applied conservation of mass for an incompressible fluid, you end up with the velocity of the inlet times the area of the inlet is going to be equal to the velocity of the outlet times the area of the outlet. But wait a second, we can put the area of the inlets and outlets in terms of the diameters, right? They'd be pi over 4 of the respective d's squared. So what does this mean? This basically means the velocity of our inlet is essentially equal to, the velocity of the inlet is essentially equal to, pi over 4 d bottle squared times the velocity of the inlet is going to be equal to pi over 4 d straw squared times the velocity of the outlet. All right. So how does this help us? Well, we can essentially, we had this sort of as of yet unknown velocity of our inlet, which we're treating as an actual unknown down here. But if we solve conservation of mass for the velocity of our inlet, then that means we can put this entire term, both the inlet and outlet velocities, we can express just in terms of this one unknown velocity of the outlet, which is the unknown that we're ultimately going for. So, our goal is, as we're churning away, cutting out and dealing with terms in this conservation of energy equation, our goal is to work it all the way down towards a single equation with one unknown V out in it. We'll see how far we can get. So, when you solve this equation for V in, you basically get V in equals d straw squared over d bottle squared. V out, units work out, and then we can plug that in right here. So what does it look like when you plug it all the way in? You have your viscous loss term is equal to 1/2 times, so V in squared, when I square this, I get d straw over d bottle to the 4th times V out squared minus V out squared plus G times H plus L. All right, now we've squared away our all the kinetic energy terms, and we've got it entirely in terms of our unknown but yet to be determined velocity of our outlet. And now it's time to make a little bit of progress on this viscous loss term. But before I do so, let's think about the relative magnitudes of these terms. So take a moment, pause and ponder. What is the order of magnitude? What is the order of magnitude for this term? Pause and ponder. this d straw over d bottle to the fourth. What order of magnitude are we dealing with here? Well, perhaps you've had a chance to pause and ponder. Maybe looked back in the in this thing right here, and it turns out that it's approximately equal to 5 times 10 to the minus fifth. And if we think about it, we have basically this term with 5 times 10 to the minus fifth out front, and this other term right here where there's basically a 1 out front. So I'm thinking 5 times 10 to the minus fifth. Like, do I even need to bother including this term? And the answer is basically no. You know, because this term out here is so small, I'm not even going to bother including this term in my further calculations. You know, just it's not even worth the algebra to carry it through. So I'm just going to keep the rest of it in terms of V out. So what do we have here? We have our viscous loss per unit mass is now going to be equal to minus 1/2 V out squared plus G times H plus L. So now we've made some pretty serious progress in conservation of energy. The only thing we have left to do is square away our viscous loss terms and hopefully put our viscous loss in terms of V out and other constants that are known. So now let's look back in our notes. So if you dust off your notes, you remember that if we assume the only viscous losses are from the pipe, right? If we sort of neglect any of the viscous losses that might occur in the bottle on the way to the pipe, you know, from the fluid entering the pipe, you know, from the fluid exiting the pipe, if we sort of neglect, you know, all of those viscous losses and say, hey, you know, any viscous losses are really just this viscous loss that occurs in the actual pipe itself. If we make that assumption, then basically the viscous losses entirely are just whatever viscous losses would occur in a pipe of length L and diameter d straw. And we have an equation for that, right? If you dust off the notes from last time, there's an equation that basically says for viscous losses in a pipe, and it's 4F. We'll leave F, this fanning friction factor, an unknown as of now, times the length of the pipe over the hydraulic diameter of the pipe, times 1/2 the average velocity in the pipe squared. So this was the viscous loss per unit mass of things flowing through a pipe, and you know, strictly speaking, there might be some other small viscous losses, but we're going to say this one dominates over the rest of them, and that's generally a pretty good assumption, you know, provided your pipe has, you know, some appreciable length. So what does this mean? Well, we can actually put some of these things in this viscous loss pipe term in terms of known constants that were given to us in the problem. So what does that mean? We now have minus 1/2 V out squared plus G times H plus L equals 4F, which we haven't yet dealt with. So I'm just going to leave it as is, as a to be determined thing here. L is the length of the pipe, and that's a known constant right here. The hydraulic diameter of the pipe is just the diameter of the straw right here. Remember, for circular pipes, the hydraulic diameter is essentially the same as the diameter itself, so this is going to be d straw. And then we have a 1/2 V squared, and whatever this V, this velocity in the pipe, well, whatever fluid velocity, whatever average velocity we have in the pipe has got to be the same as the fluid exiting the pipe, right? You know, the fluid doesn't all of a sudden like radically change after it leaves the pipe. You know, basically we have some velocity of the fluid in the pipe, that's the same as V out. So the average velocity of the fluid in the pipe is just 1/2 V out, and it's average velocity squared, so we square that. All right, what does this mean? What we have on our hands here is an equation where we have almost entirely in terms of knowns. The only thing we haven't dealt with yet is this friction factor right here. So what are we going to do with our friction factor? Well, let's for now pretend we know it, pretend it's a known constant, and we'll just solve for what our Vout would be, if hypothetically the clouds opened up and Professor Lannin's face came through and told you what F was, and then the clouds receded and you could proceed as if you knew it. So right now we're going to pretend that we know 4F, and I'll give a strategy for finding it in just a minute. So let's say we take this equation, we solve it for Vout, pretending that we knew what 4F was, and there we have it. So when you do that, you end up with Vout is equal to, we have it on both sides of the equation, we solve for it, end up with Vout is equal to the square root of 2 times G times H plus L all over 1 plus 4F times L over D straw. All right, so this is our result here. So what might be some sensible things that we do when we get to some result here? Again, we're going to pretend that this is known for now. Well, one sensible thing is to check units. Right, so if we check units, what does that leave us with? Well, Vout has to have units of meters per second. The right-hand side also hopefully has units of meters per second. So 1 is dimensionless, F is dimensionless, and then L over D, we have meters over meters. So the denominator is entirely dimensionless as well. The numerator, we have 2G, G is meters per second squared, and H plus L would have units of meters. So we basically get meters per second squared times meters, so that's meters squared per second squared. When we take the square root of it, we end up with meters per second. So the units check out. Another sanity check is to look at what happens to these various terms. So if G gets really big, then we would anticipate our outlet velocity gets big, and that makes sense too, right? The more we have gravity, the more gravity is going to get that fluid going. The more potential energy the fluid had to start with. As H increases, we expect Vout to increase, and that makes sense, right? If we have a deeper fluid here, then we sort of have more, at some intermediate point, more pressure pushing that fluid along. If H is higher, then the fluid starts with more kinetic energy before it goes and exits the entire system, right? So the bigger H is, the more kinetic energy, or the more potential energy the fluid starts with. So the bigger H, the bigger Vout. And then in the numerator, we have an L, but also we have an L in the denominator. So the L in the numerator is basically more potential energy, but the L in the denominator basically says there's more viscous loss. So basically what's going on here when we add the straw, we essentially give the fluid more potential energy by the time it exits the system by having a straw with some length. But adding a straw and having some appreciable length of the straw does increase the viscous losses as well. So it makes sense to have an L both in the numerator and denominator, the numerator giving it more potential energy to give it more Vout, but in the denominator having it sort of reduce the velocity by having more viscous loss. So L giveth and L taketh away, the diameter of the straw basically being in the denominator here, which don't worry about that too much for the time being. We'll deal with the dependence on the diameter of the straw in just a second. So this result makes sense, but what is probably still bothersome to some of you is you can be like, hey, you might be patting yourself on the back for solving for Vout, Professor Lannin, but if this 4f is unknown, you really haven't solved the problem. So, what's the deal? So what's potentially problematic about this formulation? Let's see. Well, I said pretend you know 4f, but some of you might see that there's a problem. Problem? Again, my memes are mostly 2008 era. It's an old meme, but it definitely checks out. Is there a problem? Well, yeah. If you remember, if you dust off the notes from last time, friction factor depended on Reynolds number. Reynolds number, friction factor depends on Reynolds number. Reynolds number depends on the velocity of the fluid in the tube. And the velocity of the fluid of the tube is Vout. But the outlet velocity through conservation of energy depends on the friction factor. So we basically get stuck in this unfortunate loop where in order to know the friction factor, we need the Reynolds number. In order to know the Reynolds number, we need the outlet velocity. In order to know the outlet velocity, we need to know the friction factor. And we can't just, we can't start anywhere. We have this sort of chicken and the egg problem. So, what's, how do we go about solving this? Well, a lot of times you can just make an assumption about one of these. So our strategy is, when we're stuck in a case like this is use this equation and break the cycle by making a guess for one parameter. Let's say make a guess for the Reynolds number, or make a guess for Vout, or make a guess for friction factor. Just make a guess for one of them. So make a guess for one parameter, and then proceed as if that were the ground truth. So make a guess for one parameter, proceed as if true, calculate the next, and so forth, and iterate until converged. So what does that mean? So our plan is we're actually going to make a guess about f right here. We're going to plug that into this equation to get a temporary guess for what Vout is. Use our temporary guess for Vout to calculate Reynolds number. Use Reynolds number to calculate a better, more accurate version of what f is going to be. Then use this updated f to calculate a better guess for what Vout is going to be. Use that better guess for what Vout is going to be to calculate a better version of what Reynolds number is going to be. Use that more accurate version of Reynolds number to calculate a more accurate version of f, and so forth. And you can imagine, like, this gets pretty tedious. How do you know when to stop? Well, basically once your answer is out to like the third or fourth or fifth decimal place and not really changing anymore, once you're out a couple of decimal places, then you can stop. You can stop once you've reached sufficient accuracy for your engineering purpose. So let's go ahead and do those iterations. So I like to organize this in the form of a chart. And I like to sort of have rows of my chart be sort of what iteration I'm on, and columns of the chart be particular values, either of F, Reynolds number, or V out. So let's make a chart. So I might put my iteration number. We're going to start at iteration 0. Then we'll have friction factor. And I said we're going to start with a guess for friction factor. Then we're going to use that guess to calculate V out. And the way I do this, the way I go from friction factor to V out is through this result from conservation of energy. So from our conservation of energy result, we'll go from friction factor to V out. From V out, we'll be able to calculate Reynolds number, and we'll do that via the equation Reynolds number is equal to rho times V times D over mu, right? And in this case, it would basically be equal to our known rho times our sort of current guess for what V out is, times our current guess for what V out is, times the diameter divided by, and this is basically going to be the diameter of the straw, times all of that divided by the viscosity of the fluid, right? So we can basically use F to calculate V out via our conservation of energy. We can use V out to calculate Reynolds number via the definition of Reynolds number. And then we can use Reynolds number to calculate the next iteration, the next guess for F, the next row's F, via the Moody diagram or one of the equations. Via Moody chart or equations from via equations from notes. For example, like there was one that had laminar and one that had turbulent for flow through pipes. So this is our plan. So let's so I'll include some calculations that I did here. So the calculations that I have in this version of the chart, I believe are for these calculations are for the length, the 14 centimeter length, and the full height. So the calculations that I'm using to populate this one are when L and H were these two values here, and of course the rest of the given parameters are the ones here. So so what's a sensible friction factor to start with? Well, you can't. This isn't going to always work, but this might work a lot of times. You know, a lot of times if you were solving problems in mechanics or dynamics or things like that, you might start off guessing or making an assumption of a spherical cow in a vacuum, or you might make an assumption of no friction, right? So let's basically say, hey, we don't know exactly how this system is going to play out. We don't know exactly what this friction is going to be in this tube, but as a first guess, let's just basically say, hey, let's assume there's no friction in the tube, see where that gets us for our V out, and then proceed from there. This assuming friction factor equals 0 isn't always going to work, but it turns out to work pretty well in this problem. If it's in other cases, you can just sort of assume that the friction factor is some value kind of in the middle range of what you see on the Moody chart, and that tends to work out pretty well too. So, but for now, I'm just going to assume that it's 0. If you take F equals 0, plug it into here, plug in your known constants into here, and calculate V out, you get 2.65 meters per second. So V out, I'm just going to put all of them in terms of meters per second. Then if you put this 2.65 meters per second right here, and density, viscosity, and diameter of the straw. And right here, you get a Reynolds number of 16,000. So take a moment now, pause and ponder. How can we use this Reynolds number to calculate the next friction factor? So pause and ponder. You might need to go back in your notes. Well, hopefully you've had a chance to pause and ponder. So if you've had a chance to pause and ponder, our next guess for the friction factor, well, first it would be informed by the Reynolds number. A Reynolds number of 16,000 is much, much greater than the 4,400 turbulent limit. So what does this mean? Our flow is, based on our guess of F, our flow is probably turbulent. If our flow is turbulent, and you look back in the notes, we can use the turbulent Reynolds number friction factor calculation, and that friction factor calculation is F is equal to 1/4 times 0.316 times Reynolds number to the minus 1/4 power. And this equation is from the notes, and it's for smooth pipes and turbulent flow. If we had gotten a laminar Reynolds number here, then we would need to use a different equation for F. And if we had rough pipes, then we would need to use the Moody chart in the book instead of this equation here. And the iteration would get a little more tedious, but meh. So we have this smooth pipe here. You can basically plug in this Reynolds number that we get right here to calculate a better version for F. And that brings us to iteration 1. It turns out that the friction factor you get on iteration 1 is 0.007. So our guess of 0 wasn't actually that outrageous. You then plug this new F into right here to give you a better estimate for what Vout is going to be. And the better estimate for Vout ends up to be 2.07 meters per second. You use this 2.07 meters per second in the Reynolds number to calculate a new Reynolds number, and it ends up being 12,400. We're still above that 4,400 limit. Our Reynolds number is a little bit lower. Unsurprisingly, the velocity dropped a little bit once we started including friction. Big surprise there, right? So we plug this in. We plug this Reynolds number into the friction factor correlation because this equation is still valid because we have turbulent flow in a smooth pipe. We get iteration number 2. You calculate friction factor based on that, and you end up with 0.0075. Wow, we're definitely really homing in on something here. Velocity changes to 2.04, and the Reynolds number changes to 12,200. So at this point you can be like, geez, I'm out to the third significant digit. I'm like within 1% right here. So after 2 iterations and a not even that great of an initial guess, we ended up, we converged to within a couple percent. And if you truck it all the way down to, let's say, iteration number 6, your outlet velocity is 2.0376. So even if you churned away for a whole bunch more iterations, you would still round up to 2.04 with your result. So that's this result here. So yes, you need to iterate. Yes, it's a little bit of a pain in the butt. Yes, we kind of need to be uncomfortable with making a random guess. Sometimes an ill-informed one, but after a few iterations, even with a so-so guess, we get to within a couple percent of our final result. So let's go back to the problem statement where we had 2 different lengths of pipe lengths of straw that we were considering, and a couple of cases. The case where it was really full, the case where we were somewhere in the middle. The bottle was somewhat half empty, and then the case where the bottle was nearly all the way empty. So, and let's kind of build a chart for those 6 scenarios. So, let's have 2 columns, one for the length of one where the length of our tube is just 1 centimeter, and one where the length of the tube is 14 centimeters. And then let's have 3 rows. The first row where we're almost full, where the height's 22 centimeters. The next one where we're half full at 10 centimeters, and then where we're almost empty at 4.5 centimeters. And again, it was a little tedious, but I went ahead and did this iteration process not just for the H and L of 22 and 14, where I got 2.04 meters per second, right? So this is all of the entries in this chart are going to be our V out. So, we did this iteration process and got it for here. I repeated this iteration process 5 more times for these different combinations of L and H, and ended up with 2.07, 1.43, 1.01, 1.65, and 1.43. So, what are some key takeaways from this process? Well, perhaps you observed qualitatively that at the beginning they start off almost at the same speed as one another. So they start at roughly equal speeds, and that's basically somewhat just conveniently the extra potential energy that one of them that the long straw one gets turns out to be perfectly counteracted by the increased viscous losses from the longer straw of the other one. So it turns out that both short straw and long straw at the very beginning are draining at about the same speed as each other. But then we know once we get towards the end, long straw is faster. And than its short straw counterpart. What's the rationale there towards the end? Well, basically, once the bottle is drained most of the way for the long straw, we still have a decent amount of potential energy left from the straw. But if I compared this to a short straw that was nearly empty, then I would have lost, I wouldn't have hardly any kinetic or any potential energy left. So even when the long straw is mostly empty, I still have a lot of potential energy left from the long straw. But on the short straw, once that bottle's empty, there's basically no potential energy driving it anymore. So if I compare this to these numerical results that I get for velocity, the long straw is faster at the end because it still has some potential energy left in the system, whereas most of that potential energy is gone for the short straw. So hopefully you've found this example illustrative in terms of this bottle draining problem. So thanks for watching, and good luck with your studies of fluid mechanics. Bye. Bonus minute. So you thought you were going to get away without me tying this into bioengineering in some way. Not so fast. So it turns out that this bottle draining thing isn't just something that's contrived to illustrate conservation of energy. This is something that real life people use to save human lives. So one time I was in the hospital with someone, and this person had lost a lot of blood, and the person was in fact right about to pass out from losing so much blood. So here's the person. I'll draw a frowny face because that's what they were like at the time. And they were there, sitting on the hospital bed, and they had an IV with some fluid in it. And basically, like they were losing a lot of fluid, and so what the doctor did is the doctor came over, took the IV bag, and lifted that IV bag up as high as she possibly could, as basically on the very, very top rung of the rack. And the rationale was basically by raising this IV bag really high, we would increase the flow of IV fluid back into the patient to basically counteract some of this blood loss that was going on. So, L matters for lives. So hopefully this gives you some relevance in terms of bioengineering. That I didn't obviously stop the doctor in the middle of the room right there to be like, hey, wait a second, this would make a great example for conservation of energy, but I filed it away. So fluid mechanics saves lives.